I started recording.
Okay, does it save on, it saves on your computer then, and then I
Yeah, then I can send it to you. Juan Pablo, do you want me to record for you also?
Yes, yes, please.
Okay.
Thank
Both
you.
of you should be.
Okay, I've got 9 o'clock if you want to go ahead.
Okay, Dr. Man. So welcome everybody to our Tectonics seminar. We just came from the spring break. I hope that everyone enjoyed his spring break. Today in week 10, we have Daniella Gutierrez Easley and Juan Pablo. Daniella will be speaking first about hydrocarbon potential of source rocks from Trinidad to Guyana, an application to ultimate expellable potential, EUP, acme modeling. So Daniella, can you share your screen, please?
Yes, I made the screen too small and the share screen icon went away. I'm doing it now. Okay, so just to check, we can see the right slides over here.
Yeah.
Okay. So thank you, Mohammed, for the introduction. So my name is Daniella Gutierrez Easley, and today I'm going to be talking about some of the trends I've seen between Trinidad and Guyana when looking at ultimate expellable potential or acme modeling. So these past couple weeks, I have been preparing my image abstract for the conference in August. So what you're seeing today is kind of like an extended version of that extended abstract. So I'm really looking for any kind of suggestions that I can get from you all, any comments, anything you found confusing. It all just works to make my project more sound in the future. So please don't hesitate to let me know, or my email is kind of hidden down here. I can turn on the laser pointer. Point being, just don't hesitate to let me know if you have any questions or comments. So in this area, generally what you've heard me talk about in the past are the source rocks across northern South America. Today, we're going to focus in on Trinidad and Guyana. Especially with Guyana, I think it's got like 11 billion barrels of oil to its name right now. There's huge hydrocarbon potential in the area. With that, we still don't fully understand source rock continuity, the relationship of source rocks to one another, their chronostratigraphic relationship. So the method by which I'd like to attack the problem is with UEP modeling the hydrocarbon potential of individual areas across the study area. The whole point of this is then to use these patterns that we see between the two areas to identify modes of organic deposition and preservation. So here's just some fun pictures over here on the side of Conje Formation core from Guyana, and the famous Naparima Hill Formation outcrop in San Fernando, Trinidad. And somebody correct me in the comments if I'm wrong. I think this is a national park in Trinidad, but a really famous outcrop. So like I said, I like to bring in suggestions I get from previous semesters. And one of the things that I heard from my friends that came to the seminar last semester was that I just dive into acronyms and I kind of explain them at the end, and maybe it's out of order. So I thought this time around, I just go ahead and define these terms that I'm going to be using pretty much over and over again. So acme is the first one you'll hear me say, and an acme is a moment of maximum deposition. This may be a figure that you saw in like a biostrat or a paleo class, but that acme would occur. Here they have it kind of spread out, but really it would just be the point in the middle of maximum deposition. An acme time interval is the million-year interval that encompasses an acme, and even an acme time interval is equivalent to a million years. the reason that we don't just refer to million-year intervals is because acme, time interval, has a very strong connotation towards deposition, understanding the rate of deposition at an interval. So the next one I'll talk about, UEP, it's in the title, Ultimate Expellable Potential. And this is the total volume of hydrocarbons a rock could produce under absolutely ideal conditions. So regardless of its thermal maturity history, what's the volume it could produce just based on organic chemistry. So keep in mind that many of the rocks that I'm looking at today, they've already produced hydrocarbons. So it's kind of a backwards work to go back in and add those lost hydrocarbons back into the UEP value. Two things you've probably heard of, just in case, TOC and HI. TOC is the total amount of non-inert carbon, meaning the carbon that's able to bond with hydrogen to form hydrocarbons. Similar thing going on with the HI, it describes the amount of, not technically free hydrogen, but the hydrogen that is available to bond with the carbon. So this don't want to call it an attempt, but I see a trend of trying to describe source rocks by TOC. What defines a good source rock? What type of TOC? And the point that I want to make here is that hydrocarbons are made of carbon and hydrogen. So if you don't have both, you won't get hydrocarbons, meaning it's not all about TOC. You can have great TOC, but without HI, you're not getting oil. On a similar note, we've got TOC not and HI not. So I mentioned that we're doing a lot of reconstruction. These rocks have already produced hydrocarbons, so we're working backwards to understand their initial conditions. And in the reaction to produce hydrocarbons, hydrogen and carbon are consumed. Those are the reactants in the reaction. So we need to back calculate these values to understand what the organic components of the rock were like before anything was generated or these molecules were consumed. Last one I'd like to mention is OAE, and I have a whole slide on that that's pretty similar to last semester, so I'm gonna speed through this and add just a few new comments to it. So oceanic events are extremely large global events that are commonly cited as a driver of source rock potential. It's a cyclic function, so we've got a lot of different OAEs, some large, some small. Small still being relatively large, but the one that I'm focused on today is here at the Cenomanian Turonian. This is OAE2, or the Bonarelli event at 93.6 million years ago. And here's just the explanation again I showed last semester of what's happening during an OAE. Anoxic is in the name, so if you guessed it, the main point is that it causes in certain areas very anoxic bottom waters. And that's through changing essentially the water stratification of the region. So this is also a diagram that I had last semester, but I have been kind of looking at it in a new light I wanted to show you. So if an OAE, or specifically OAE2 here, is responsible for source rock potential, is immediately responsible for source rock potential, we'd expect that we would be seeing like a peak right here, right at the OAE2 marker. And this is UEP on the y-axis. So in this Gulf of Mexico example, we're actually seeing a spot of organic lean source rocks. So an immediate thought could be, all right, there's no way that this OAE is responsible for source rock potential because we see an inverse relationship. But a couple of people have kind of brought this up in conversations with me. Imagine the case where there was a basin that was restricted. It was a restricted basin during the initial occurrence of the OAE. An OAE only really lasts plus or minus 0.5 million years, but some of the effects can still linger up in the atmosphere and in the bottom waters. So this basin A, was restricted and later opened up. It could feel lagged effects of an OAE. So we can't necessarily say just based on a diagram like this that the OAE has to do with source rock potential. So the reason that I bring this up is I think it's just a really strong example of why it's so important to understand the tectonics and the geology of the area if we have words like OAE, and we try to understand the mode of deposition. Okay, finally to the study area. My work is typically focused on this whole study area map, but like I said, today we're going to go in on Trinidad and look at 4 wells in the southern end. We also have 6 wells in Guyana. One is ambiguously located on the nearshore Guyana shelf, and the remainder are up on the Demerara platform. So for a very, very speed review of the tectonics of the area, we've got the Central Atlantic rifting phase happens at about 190 million years ago. I feel like Kenneth is going to correct me on some of these in the comments. And then equatorial Atlantic phase occurs from 125 to about 100 million years ago, but it has this effect of transpression on Guyana from 125 to 112 million years ago, and that'll be kind of the start of our study interval. So both of these areas are in a passive margin state, except the Trinidad region is going to be reactivated. It transitions to an active margin as a foreland basin with the eastward movement of the Caribbean plate. And you can see its current location of by number 6. So for the methodology, 2 parts. One is this chronolithostratigraphic column, and the other part is creating the actual model. So the first step, what we did was we created this, started as a lithostratigraphic column because we pulled all these columns from the literature and tried to add them together in a really cohesive way. And the next step was to use, these are the tables that I'm going over in this study. We used those to slowly transition this from a litho to a more of a chronostratigraphic column. And this is just a really good visualization of the age equivalency of a lot of different rocks. So we start at the bottom. We have the first 2 source rocks that are going to pop up. There's the Couche in Trinidad and Potosi or Pitoko in Guyana, depending on whose paper you read, they seem to spell it differently. And then the intra-Albian unconformity, you're also going to see on my UEP map. So as we move up a little bit, we get the start of the Conjay Formation and the Gautier Shale in Trinidad. Those both continue still productive source rock intervals. And then finally going into the lower Naparima Hill and then the New Amsterdam in Guyana. Also point out, these are the giant turbidite systems forming that are a large part of exploration efforts in the area. So, oh, sorry about my phone. If my project is about UEP at some point, I should make a UEP model. And the way that I've done that is collecting current TOC and HI from well logs from the literature. These also have the thickness and some type of age indication. And I back calculated the TOC knot and the HI knot and completed an organofacies examination, which is typically based on inorganic geochemistry. So there's a lot of math that went into this, and I don't want everybody to fall right back asleep at 9:15 in the morning. So I'll show you that it kind of looks like this. It looks like going through the literature, finding these, any kind of data points with any kind of age, and doing a lot of math in Excel, and finally doing that and getting to the point where we can plug this into Kinect software. So this is my current working model, my current UEP result figure. And I'll point out before I dive into this, you may see an obvious difference between Trinidad and the Guyana Suriname Basin. So this, all of these is first interval. And with the 6 wells in Guyana, there was really exceptional sampling, geochemical sampling here. So especially this well 1, this was the ambiguously located well. It's got a ton of different samples. Each bar is an individual sample, and these are read cumulatively. So what I'm working with right now in Trinidad is, like I said, these older that maybe only give us 1 to 2 sample measurements per geologic age. So for example, the Campanian, I may only have 1 sample, but I have to make an assumption at this point that that geochemical quality extends all through the Campanian. So there's an unlikeliness that it does, and even based on a lot of my previous work and others, it's kind of an impossibility that it is exactly constant throughout the interval. But what it allows us to, this preliminary stage of the project, is it allows us to look at patterns still, the general patterns, the general trends that we see between Trinidad and Guyana. So looking up at the Maastrichtian, there's low UEP in Trinidad up here, but we can't yet compare it to Guyana because of lack of data. Move a little bit down into the Campanian, we see two wells, Maroc 1 and Moruga East 40 or 15, with high UEP, still no possible comparison to Guyana. First one we can compare is the Santonian, where we don't really have significant UEP in either region except for each. So the Maroc 1 showing a general oil proneness to it, and IODP 1261 over here on the Trinidad or on the Guyana side. Coniation is very important and was unexpected, but you see consistently high UEP at almost all wells in this study area. So Moruga West 45 over here does show low UEP. That's one of the exceptions. The other one is IODP 28, for which we just didn't have data for that section. Going down to the Turonian, moderate UEP across the whole region, although notably less than the coniation. But the point is, and the significant part of this is that the consistency across the whole area. Cenomanian, commonly cited as the most important geologic age for source rock potential across northern South America, shows us these terrible UEP values in Trinidad and only what we would consider significant potential in Guyana once, and that's again at IODP 1261. So for the final section, the Albion down at the bottom, in the wells where it was penetrated, we can see low to moderate UEP that is generally gas prone due to insufficient hydrogen. And finally, I'll bring up the OAEs again here, the orange line marker for OAE2. And like I said, if the OAE was directly responsible for source rock potential, we'd see this big jump right after the OAE occurrence. And we only see that in one well across the study area, IODP 1259. So those are the results. What does it mean? How do we use this to move forward? So one of the things I would have loved to have talked about, but I didn't have time to add in a slide, so I'm probably going to go over time anyway, is that we also observed a shift from organophages B to A near the Turonian coniation boundary. That's really important because of what it tells us is that there are similar paleogeographic conditions during the passive marginate that existed in both areas that are likely responsible for deposition and preservation. So it just further drives home the point of this similarity, the similar mode of deposition between the two regions. So of course, I'm going to bring it back up again. Is OAE2 responsible for hydrocarbon potential near the CT boundary? And last semester, I said probably not, but I didn't bring enough evidence. So I have brought you my top 4 reasons why I don't think that OAE2 is responsible here. The first one is the generally organic lean rocks with inconsistent gas and oil prone natures at the CT boundary in Trinidad, and very similarly, very consistent organic richness at the CT boundary in Guyana. So if you imagine these gigantic OAE, it's got global effects. It's not completely logical why it would have a strong effect on one well in Guyana, and then it wouldn't affect the well right next to it in very close proximity. So that's a second thing that makes me shy on the OAE to explain. The third one is recent studies that have come out modeling the upwelling effects that were likely associated with the OAE2 event. So down here is the Caribbean Large Igneous Province, and along with 2 other LIPs, these are cited as responsible for triggering the onset of OAE2. And the dark areas here show regions of increased upwelling, due to these events. And when we look at our study area, everything is pretty white or very, very light gray. So not a strong chance of the upwelling effects of the nearby LIP actually reaching the study area. Fourth reason is based on paleogeography. So paleogeographic maps are suggesting a more deep marine, potentially anoxic section over here in Guyana and a fan channel environment. All our wells are actually plotted. This is the Cenomanian Turonian that we're looking at. And all of our wells are plotted on these fans, which makes sense why we didn't see any potential in Guyana basically at all during the Cenomanian. But I'd like to note that these maps, they also show the boundary of basin flooding that happened during the Turonian, about the middle Turonian. So if we go back to our observation that there was an organofacies B to A shift at roughly this time, as in B to A shift means that there was an increase in clay content during the Turonian. This also lines up with the overall conclusion local paleo-environmental conditions are a more likely driver of source rock potential in the region, all the way from the Albian to the Maastrichtian. Oh, I was under time today. I'm all done. Please let me know if you have any questions, comments, or suggestions.
Thank you, Daniela, for the interesting presentation. It's time for questions.
Hi, Daniela.
Hey, Anna.
So, can you move back, please?
Sure. Let me, I have too many animations built in. Do you know the slide you?
That one.
This one?
Yes, that will work. So, you know, the oceanic event number 3 is exactly in the boundary, or is around the limit between Santonian and Conitian. And that oceanic event is due, I mean, some research said that a very huge massive mass extinction. So that will, you know, you just said that there is a change in organophages.
Oh, so that would be the change in organophases was right here towards the Turonian Phoenician boundary. So it was a little bit more to the Turonian side. Like,
Okay. So I heard something about Santonian and Conitian. You mentioned something.
oh, I see. Yeah, I see what you're saying. Maybe one of the smaller events could be, like it might not have had like the OAE2 effects, but it could correspond to that shift in organophases.
Well, but in any case, in this context, I will add information about the oceanic event number 3. So don't limit only to oceanic event number 2.
That's a good point. I'll add some of those in. Most of the time I focus on 1A and OAE2, and I haven't gone up to OAE3 yet, so that's a good suggestion.
Yeah, that's just to make a frame in the Cretaceous, right? Because we also the oceanic event number 1, but I think with those two will be more focused, at least more constrained the research.
Yeah.
And I mean, this looks good, but you know, hydrogen index, if you don't have the Tmax information, sometimes it could be useless. I mean, it's difficult to interpret the hydrogen, or to make any conclusion only for a hydrogen index. So I will take a look in the Tmax. I don't know even if you can plot it as a line on top of these. I don't know. You will find how to.
So this is a really interesting point, and I wanted to make a slide on all the math, and I went back to my proposal where I wrote out the steps of the math, because we can actually with high certainty predict the Tmax and then move through the calculations from that point. So when I wrote it out in my dissertation, in my proposal, it was 5 full pages, and I'm like, I don't know if I want to add that to the PowerPoint, but I'll gladly share that with you, because yeah, most of the time in this older data, we're missing Tmax. And so the model Tmax is what I'm using in this project.
Okay.
Yeah, it was pretty cool.
Yeah, and well, I'm sometimes also a little, you know, the kerogen type also is very important, but I really don't know how you can, in a simpler way, those variations, or maybe you don't have the data. So I don't know, just a comment.
Yeah, so we, instead of the classic, like the type 1, 2, and 3 kerogen type, we're using the shift between organophages A to B as a proxy. I would love to add that into the diagram because I can pretty much say in each well like where that shift in kerogen type is, and I think it would be better visualization if I also added it to this figure.
Yeah, that's a comment. I know it was a short presentation, but I didn't get when you explained what was a B organophage or an A organophage. I didn't get it.
That would, yeah, these are the suggestions I like. This is a point that I can add to the definitions at the beginning for next time. But I have a lot of papers that I can, or one really important paper I can on this that would explain it because I was not familiar with those either before I started this project.
Okay. Last comment, sorry. So I know it's an important difference about the amount of that you have sent this, but then it's difficult to compare. Maybe you, because you already know the data, right? But I don't know if you can maybe make an average for the Guyana samples just to see how it looks comparing to the Trinidad data.
I see what you're saying. Yeah, that would be a good middle step because currently I'm on like the opposite direction. I'm working on securing more data for Trinidad so that I can make it look more like Guyana. But maybe
that would be awesome. But if you cannot get that, maybe you can at least smooth the lines. So don't make it so you know, so
small. Yeah.
Yeah, so smooth, so it can be at least a little bit more comparable. I think working with average or
some type of normalization.
Yes, something that makes it more comparable to the eye.
Okay. Yeah, there's a lot of good points. Thank you, Emma.
Great.
Thank you. We still have time for questions if we have any questions.
I have a question. You know, you ended on the note that you thought that paleogeography was key to explain all the differences. But if you could go back to one of those maps, can you just pick 2 of your wells and illustrate that based on the location of fans and other features that are shown on here? I mean, is there some geologic explanation that you can provide here, given that some of these wells are the ones you're talking about, right?
So I was more using the paleogeography to explain just the specific differences that we see at the CT boundary, and then also use paleo maps to explain post-Turonian why everything is so incredibly similar from that point. So what I think is going on is during the Cenomanian Turonian boundary over here in Guyana, these are the exact like 5 wells that I have up on the Demerara rise, and the other one would have been kind of over here. Or sorry, I don't have my pointer on how well you can see this.
I can see it. Yeah, go ahead.
And then the wells that I used in Trinidad are right here, the Morne Diablo 34, the RP1, the Maroc 1, Maruga E 45, and those are the ones that are plotted on here. So I'm just citing mainly the difference between a location in this submarine slope fan channel system in Trinidad, and then this would be a more like high TOC shale depositional deep marine environment in Guyana. And so I think those differences can account for the differences at the sea, which is backed up by this a giant, large-scale basin flooding that happened in both areas at the same time in the Turonian. So the way I consider that basin flooding, and correct me if I'm off on this one, is that it was kind of an equalization of paleogeography that happened in both areas. There was kind of a normalization. So the paleos were different during the Cenomanian, but during the Turonian, they largely, at least for some amount of time, became very, very similar. And I think that ties back in with the observation that beginning Turonian and post-Turonian, the pattern and UEP are essentially the same in the two areas.
Okay, got it. Good.
Daniela, I have found at least 2 papers that they said that the oceanic event number 2 is not related to Caribbean lip.
Really?
Yes, so because there is a gap between the timing among one and the other. So I'm gonna try to remember which one are, and I will try to send it just for you to be aware if someone asks you in the future.
Yeah, for sure. I'm really curious about that. The one that I read was that Bergman paper, who was just tying the Caribbean lip to OAE too, but it's obviously good to have all the information, you know.
Yes, yes.
Thank you.
Thank you so much. Thank you, Daniela, and thank you for the questions. The second speaker is Juan Pablo Ramos Vargas. He will be talking about effects of the Panama arc-indenter on the distribution of hydrocarbons in northwestern South America. Juan Pablo is a first-year PhD student at CPTH, and also he is the vice president of the AAPG Wild Cutters, so people can reach him for future talks and speaks. So Juan Pablo, can you share your screen, please?
Yes, Mohammed, thank you. Please let me know when you see my presentation.
Okay. Yeah, we can see.
Okay. Okay, thank you. So, thank you, Mohammed, and good morning, everyone. My name is Juan Pablo Ramos. I am a PhD student in geology at the University of Houston, advisor Paul Mann, and also research assistant at the CBTH. And today I'm going to present part of my research, effects of the Panama arc-indenter on the distribution of hydrocarbons in northwestern South America. So the area of study of my research focuses on the junction of the South American, Nazca, and Caribbean plates and their interaction with the Northern Andes and the Panama blocks. In this figure, you can see that the Nazca, Panama, and Caribbean plates are converging against a relatively stable South America. And because of that, this Northern Andes block is moving northeastward along this Bacanal fault system. To this day, there is much debate about the age of the Panama block collision and the regional effects that it had in northern South America. That continuing debate about the tectonic event is shown in this slide, because this event had a dramatic repercussion on global oceanography and migration of terrestrial faunas. It has been well studied from different perspectives, but these previous works by different disciplines have interpreted different ages of the collision. So please observe that published papers based on geological records have interpreted collision ages as early as 25 million years ago, while ages interpreted from molecular and paleontological records assign a more recent age since the Pliocene. So for this reason, the objective of my research is to analyze the timing of this tectonic event, the regional effects of the Panama arc collision, and finally assess its repercussions on the distribution of hydrocarbons in Colombia and Western Venezuela. So for this purpose, 4 lines of evidence were studied. First, the subducted plates in the region from the distribution of earthquakes, volcanoes, faults, and location of tectonic tears. Second, and in lift of basement blocks in the region based on thermochronology, paleogeography, and biological reconstructions. Third, studying the age of subsidence in clastic wedges from burial plots and sediment thickness maps. And finally, comparing all these results with the current distribution of oil and gas in the region. So to analyze the geometry of the subducted slabs, I plotted the distribution of earthquakes since 1980 and assigned colors according to the depth of the hypocenter. So it is important to note that here at a latitude of 5 degrees north, there is an offset of approximately 240 kilometers, which has been called the Caldas tear. This tectonic feature represents a displacement of earthquakes towards the east and represents also the end of volcanism in Colombia to the north. So in this way, the Caldas-Tier has been interpreted as the possible boundary between the Caribbean and Nazca domains, while Panama behaves as a rigid indenter that deforms the crust in between, with this marked zone here with no seismicity, but also with a seismic nest called Morindo in the zone of the collision. So in this slide, I'm going to show you two sections of the study area showing the changes in plate geometry to the south and north of the Caldas-Tier. To the north, the low angle subduction of the Caribbean plate, ranging from the subduction zone in the southern Caribbean, the Fort Bell, to the eastern Cordillera, while the Nazca plate is subducting at a steeper angle to the South American Trench on the Pacific margin of Colombia. So consequently, this intermediate zone between the two corresponds to the Panama rigid indenter, and the southern boundary, that it's the Caldas-Tier, defines this change in subduction geometry, therefore in the deformation of volcanism in the whole region. When we analyze the potential methods in our study area, we can see that from gravity, an evident increase in the width of the Andes occurs north of the Caldas-Tier, aligned with the location of Panama collision. And for the magnetic methods, it was also possible to identify the approximate location of the Panama indenter from this bimodal response in the magnetic anomaly that was first interpreted by other authors in recent years. So when we look at the general strike of the structures and the magnetic anomaly, we see a marked change from south to north once we reach the indenter zone north of the Caldas-Tier, which we interpret as lateral deformation associated with the collision. However, for our study, it is essential to know the time when this deformation occurred. So for this purpose, thermochronology is a very useful tool because it measures the age at which some minerals were cooled, which is directly associated with uplift. So the important thing I want you to keep in mind here is that the green dots are associated with apatites that show a greater phase of cooling, and that means a greater amount of uplift. So what we are going to see is the approximate sequence of uplift of the basement blocks in the northern Andes. And what we see in general is that by the late Oligocene, the western and central Cordilleras had already been lifted considerably, while the eastern Cordillera still had a slower rate of cooling and uplift. As we continue with our reconstruction, we can observe how from the middle Miocene, approximately 15 million years ago, the eastern Cordillera have a considerable uplift rate with the increased presence of these clusters of the green points that are from the apatite, and this transition from west to east shows the progressive uplift of each of the mountain ranges in Colombia. Finally, for the late Miocene to the recent, we can see a major and generalized uplift of this eastern mountain range, which has been associated by several authors with the collision of Panama to the west. So please look in this slide, our interpretation of how the collision of Panama arc since the middle Miocene is responsible for this widespread uplift during the last 15 million years. Based on thermochronology, we associate the uplift of basement blocks and lateral deformation as a consequence of the collision of Panama to the west approximately 12 million years ago, an age that aligns with the interpretation of previous authors such as Anthony Coates in 2004, based on paleoenvironments of sediments in the Panama Canal. In addition, we also include here this figure showing how radiometric ages north of the Caldas-Tier also show values of approximately 15 to 5 million years ago that were attributed to the same tectonic event by Kellogg and others in 2019. For our study, the first depth to basement map of the entire region was rated based on interpretations published in the last decades, which allows us to observe the main basement blocks that have been uplifted and also the main sedimentary basins in the region. Paleomaps are currently being prepared for evolution of the positional environments in the area since the Eocene that were affected by all the tectonic evolution of the area. So in general, what we can observe from this map is that until the early Miocene, there were still deep marine depositional environments between Colombia and Panama that was finally uplifted and closed since the late Miocene. These maps have been particularly useful for analyzing and understanding the evolution of drainage systems in the area that transported the clasts eroded from these uplifted basement blocks and formed some of the main elements of the petroleum systems in the region. So the Magdalena and Cauca river systems that are the main fluvial systems in Colombia drain into the Caribbean, were formed since the middle Miocene as the uplift occurred due to the collision, and aligned these drainages, these rivers, in the entire region in a south to north direction. In addition, the age of this uplift has also been evidenced by ecological reconstructions in Colombia and by analysis from the Great American Biotic Interchange between North and South America that occurred in association with the formation of the Isthmus of Panama. So these reconstructions that were elaborated by Jaramillo in 2018 showed that by 10 million years ago, the formation of the Andean South American forest began to occur due to a regional uplift event where previously only the presence of tropical South American rainforest was evident at lower altitudes. We have attributed that in the last 10 million years, these paleoecological changes that produce these grasslands and savannas that previously did not exist in the region are directly related to the continuous uplift that was produced by the Panama collision for this time, as it was observed by thermochronology. Additionally, here in the image on the right by Bacon and others in 2015, it can be seen that the exchange of fauna between North and South America, you have here the migration rate that included large mammals, peaks approximately 10 million years ago, which needed a terrestrial connection resulted from the collision of Panama with South America. So this 10 years aligns with all the results we have seen so far. So now, in our depth basement map, we observe with these white dots, the clastic wedges, the sedimentary basins were burial plots elaborated to understand how sediment transport and subsidence occur in the region. So this analysis was divided between the onshore and offshore sedimentary basins. For the sedimentary basins in the continent, it was observed that for the Llanos Basin foothills, the Middle Magdalena Valley, and the Catatumbo, the three most important basins in Colombian petroleum history, there is a pronounced event of burial for the Middle and Late Miocene, especially in the Llanos foothills and the Catatumbo basins to the east of the uplifted Eastern Cordillera. For the Chocó area here in the Pacific margin, there is also a marked subsidence record for the Miocene-Pliocene phase associated to loading of sediment from the eastern mountain ranges. Continuing with the burial plots, when we look at two of the clastic wedges contiguous to Panama, Urabá and Lower Magdalena, there is an evident phase of subsidence that is observed since approximately 12 million years ago and through the late Miocene-Pliocene. Especially remarkable is the Urabá Basin, whose formation is directly related to the collision of Panama Arc and shows a formation since 14 million years ago, which allows an estimation of the timing of the collision here to the west. In addition, for the analysis of the burial plots, it was important to take into account the clastic wedges of the Caribbean. So in this slide, we can see how for the Maracaibo Basin in Venezuela, there is a very marked phase of total subsidence from the Miocene to the Ricine associated with Andean tectonics and the flooding of clasts into the basin north of South America in the last 15 million years. And here for the Ranchero Basin of Guajira Peninsula, the same result was obtained by observing the main burial phase associated with sediment loading during the Miocene-Pliocene stage. When we move westward along the Caribbean margin, we find that for the Cuisa Basin in Guajira offshore and also near the Chuchupa platform, the only place where so far hydrocarbons have been produced commercially in Colombia offshore, we see a formation of clastic wedges since the Miocene with marked subsidence events for the late Miocene. For the Magdalena Submarine Fund, we also obtained the same analysis, a clastic wedge formation since the Miocene with marked subsidence by sediment loading for the late Miocene-Pliocene and with more than 10 kilometers of sediment thickness, making it the zone with the greatest thickness of sediments in the whole area that is related to this Magdalena fluvial system that was developed from the uplift of the basement blocks on the continent. And finally, when we move into deeper waters in the Columbia Basin, we again see a final phase of pronounced burial into Ricine in this clastic wedge, and which has a particular importance due to the presence of Cretaceous rocks buried at interesting depths for hydrocarbon generation since the late Miocene. In this slide, I will show you two seismic lines along two of the previously presented clastic wedges. So the first one here corresponds to a seismic line along the Llanos Basin, that is the most prolific sedimentary basin in Colombia. We can see how the sequences since the middle Miocene here in orange represent a tremendous sedimentary load, resulting from the deposition of clasts that come from the uplifted basement blocks. And this had a direct implication in the generation of oil and gas since the Miocene in the foothills of the Llanos Basin. This seismic line below corresponds to the Columbia Basin in deep water. It's one of the areas with the greatest exploration potential in the country in the coming years, where it is observed how the Miocene and Pliocene sedimentary sequences represent most of the sediment thickness in the basin. This thickness is directly related to the large amount of clasts coming from the Magdalena fluvial system that, as we saw, is formed since the Miocene related to the uplift produced by the Panama collision. So for that reason, the petroleum potential of these offshore Caribbean basins are directly related to this tectonic event in the Miocene that produced this flooding of sediments to these clastic wedges as we saw on the burial plots. The map that you see here in this slide corresponds to a sediment thickness map where the greatest thicknesses are in green color, and this corresponds to the classes previously presented, such as the Columbia Basin, the Maracaibo, the Middle and Lower Magdalena Valley, and the Llanos Basin here. This shows that the areas with the greatest sediment thickness in the entire region and with greater potential for oil and gas exploration are directly associated with sedimentary basins that were flooded with clasts since the Miocene as a result of the erosion of basement uplifted during the last 15 million years in the entire region of the Northern Andes. And finally, returning to our map at the top of the basement, where we observe the main uplifted zones and sedimentary basins, we will see the current hydrocarbon distribution in the region. So here, this map shows the distribution of oil and gas seeps in the northwestern corner of South America. An important feature I want you to notice here is the change in the occurrence of seeps when moving from south to north of the caldastir, and an apparent migration of these points to the east once we are in the area we define as the inter. An additional element that I would like to highlight is the presence of these seeps in the Pacific margin and in the Sinu Belt, both areas that have been little explored so far, but which show oil potential for Colombia. And additionally, when we plot here in red the oil and gas producing wells, we can observe that the Panama indenture is a hydrocarbon poor zone related to the uplift of the basement, but also with this figure, it is possible to observe the most prolific areas for hydrocarbons so far in the region. So the Maracaibo Basin in Venezuela stands out, which is closely related to the late Miocene uplift of the Merida Andes and the sediment contribution to the basin, as well as the foothills of the recently uplifted Eastern Cordillera, showing the great importance of the Panama collision tectonic event in the distribution of hydrocarbons that have been found so far in Colombia and Venezuela. Other basins, such as the upper, middle, and lower Magdalena Valley, as well as the Catatumbo, observed in the burial plots, also stand out for their production. Also, furthermore, what we observe in the presentation allows us to have confidence in the potential of areas such as the Columbia Basin and the offshore Caribbean margin in general, due to the constant flow of sediments that we observed since the late Miocene, related to the development of the Magdalena and Cauca fluvial systems and the erosion of basement blocks that flooded these clastic wedges. So to conclude my presentation, a few concrete ideas to take home. From subducted slabs and potential methods, it is possible to see a regional deformation pattern when we go from south to north of the caldera. We associate to the rigid Panama indenture. From thermochronology, paleogeography, paleoecology, and burial plots, we can determine a collision age from middle to late Miocene that fits with previous studies, and this event had marked effects in the uplift of basement blocks and consequently in the flooding of sediments toward clastic wedges generating subsidence. And finally, that the Panama collision had a direct influence on the distribution and maturation of hydrocarbon region, generating hydrocarbon poor zones where the basement was uplifted, but also prolific zones due to the sediment load that had fed several sedimentary basins since the middle and late Miocene. Thank you very much for your attention, and I remain attentive to any question or discussion in this regard.
Thank you, Juan Pablo, for the interesting presentation and figures too. We have time for questions.
Hello, I have a question.
Yes.
Can you hear me?
I can hear you, yes.
Hola, Juan Pablo. Hi, how you doing? It's Diego Yaja here.
Hi, Diego, how are you?
Good. I have an observation about this.
Mm-hmm.
Your state is that the deformation migration to the east is related to the collision of Panama in the caldastir region. But if you discussed this the last time, if you also see to the north, the Merde Andes, Perija, and also the uplift of the Sierra Nevada Santa Marta, what you can see is that you also said that there's a flat slab segment of the, as you plotted the earthquakes. You can see the flat slab effect in the northwest part of Colombia. Therefore, it may be also interesting to analyze both, right? That you have a segment that it might have also this effect of Panama, but the flattening of the slab, the change of the subduction from normal to flat, in Argentina, the Pampean ranges generates a broken foreland, as Teresa Jordan said. No? You have an uplift of basement core ratios to the foreland. No? This is really similar to what happens in Argentina. And it's not just an effect of the collision of the terrain, but it's the flattening of subduction. The Caribbean plate flattening produces a migration to the east. No, that's something. I don't know what you think about that.
No, yeah, you're completely right, Diego. Let me just go back here to the slide that you mentioned, where we have the earthquakes and the subducted slabs. So
there you were. You have it.
Yeah, here. So yeah, no, you're totally right. The influence of the flat slab subduction here of this Caribbean plate in the entire region is evident. I will look for the information that you're mentioning in Argentina. That could be like a good way to see the uplift of the Andes in the southern part of North America related to flat slab subduction. At the end, what we saw on our study is that this marked change here in the distribution of earthquakes and like in the deformation in the region in this place, like aligns with the position of this indenter. I think it's like a mix of both things, a mix of the flat subduction of the Caribbean plate here in the northern part, but also there is a marked effect of this indenter that pushes and deforms the crust here in between to the east. And as I mentioned, like they have interpreted the age of the collision based on paleoenvironments and sediment depositional environments for the last 15 million years. And when we look at the thermochronology and the uplift in this region, we see that it aligns with those same ages. So that's why we attribute like this whole deformation here to the west, like this change of width of the whole Andes in the northern part to the collision of this indenter right here, but it just pushes all what we're looking at here. So we also have to include like the whole influence of this Caribbean plate that it's subducting at a lower angle here to the south in the northern part of South America. But yes, thank you for your comments.
No, thank you. It's a great job. I have also a small another question. They also said that the Miocene in the Caribbean basin has a big influence of the collision and subduction. I haven't hear you, or I'm not sure about that. You said also when it starts the subduction beneath the northern part, no, of the subduction of the Caribbean plate below Panama, no, and you have like a folding, tilting, no, of the oceanic crust below, below Panama, not just below South America. That's something, that is also the starting of the subduction below Panama, but it's also what we discuss is about the sediment supply and the tilting and the folding of the oceanic crust. That's something, that is not just but the folding of the oceanic crust being subducted, not just
by the subduction. Okay.
Subduction below South America and below Panama, right?
Yes, just to ask, so you're saying that it's not only like the sediment floating, but also like the folding, like the deformation of this crust that creates a space.
The oceanic crust is being like folding in the subduction, no? As you're being subducted, as you're approaching to the margin, it bends, right?
Yeah.
So this bending generates the trench space, so you have a more space dynamic to accommodate, and you can see it here, and it's progressive moving as the oceanic crust is moving forward below Colombia and also below Panama, right?
Okay, yeah, perfect.
Thank you. Great job.
Thank you, Diego. Thank you.
Juan, I have a lot of questions. We are almost out of time. Maybe I would love to talk to you out of here. But
Yes.
so first, my first question for you, what is the mechanical function of the Panama Arc in relation to the Caribbean movement?
What we're interpreting right now, what we think is like we have the of like the whole deformation of northwestern South America since the late Cretaceous associated to the Great Arc of the Caribbean and the Oceanic Plateau. And since the Miocene, we have this arc, the Panama Arc, that collides with South America and like, I don't know how, like foster and improves the deformation to the east in the whole region. And like when we look at the thermochronology and the development of boreal plots, we can see like that marked phase of uplift and also subsidence in the whole region in these Miocene ages that we attribute to the Panama collision. Yeah.
So the Panama Arc has a different origin than the Caribbean, right?
It's the Panama Arc is like the part that comes behind of the Caribbean plate. We have the Caribbean plate that's moving eastward relatively to South America, and the subduction that we are seeing here on the on the Caribbean plate, the southwestern part of the Caribbean plate is creating this arc that is also moving with the Caribbean plate. And in the Miocene, we attribute that it collides with South America. It's like the part that it's behind the Caribbean, this arc that is related to subduction in the back part of the Caribbean plate.
So there are two, at least two that I know, two origin of the Caribbean, right?
Yes.
So you are supporting, or your version is supporting that the Caribbean comes from the
Pacific,
from the west, correct? And is coming inside, right? But then how can we have marine deep environment in the maps that you show? And go to the paleo maps.
Let me just here.
Yeah, so around, so you show deep marine environments around there.
Yes,
and I don't know how that will be possible if we have a Caribbean coming from that side.
It's because, I mean, we have like this oceanic cross, like the plateau that it's moving here northeastward against South America. But it's, I mean, if you're mentioning that Caribbean plate wouldn't be like really deep, I mean, it's a marine environment. It's an oceanic cross that right here, the arc that is placed right here hasn't yet collided with South America, like here in this region. That's why we still have like marine sedimentary phases, deep marine sedimentary phases that they have been studied here, like in this region by sedimentary studies, that they saw that for the Miocene, for example, here for the early Miocene, there was the position of marine environments that were not shallow, were deep. And when we move from the early Miocene to the present, we see like the changes here in the sedimentary record, moving from deep marine environments to shallower marine environments, and then continental, that is attributed to the prior collision here in this part of this arc that hadn't collided yet for the early Miocene. That helps to answer my question. Yeah.
Okay.
Yep.
Well, it's almost time. Yeah. Okay. We can talk about this.
Yeah. If you have more questions, you can reach me out.
Yes, yes. I'm not sure about the timing of the times that you are presenting, because, for example, we have the Andes in Venezuela, in Mérida.
Yep.
The uplift is around, what, 20 million of years ago? And then you are proposing that the Panama Arc came on 10 years ago, right? So we are, it will means that all this movement on the Caribbean happened in 10 million years. I don't know if that's, I'm not sure. I'm just thinking about the timing,
yes, no,
you know?
No, you're totally right. I just to mention what Diego was saying is also important. It's not only that everything was uplifted by Panama in the last 50 million years. We can see here on the thermochronology that all this thing was already being uplifted before. Because we have the subduction, the Caribbean plate, we have the subduction of the Farallon plate since the late Cretaceous. So we have a whole story of the formation here. It's not only Panama. So we have Farallon, we have the collision of the oceanic plateau, we have subduction of the Caribbean plate at a steeper angle in this whole region. So it's not only the collision of Panama that uplifted everything here, but we can see like in this region, it created a marked phase of the formation since the Miocene, but everything had been uplifted. If you see here, this map, the late Eocene, we have already a great amount of uplift here, for example, in the Western Cordillera and the Central Cordillera. So it's not only Panama, but a whole story of deformation and uplift since the late Cretaceous or even before.
Okay, great.
No, thank you, Anna. If you have questions, just let me know.
Thank you for the question. We have time for one question, really. Do you have any question? So thank you, Juan Pablo Ramos Vargas, for this interesting presentation, and thank you for Daniella also. I'll stop my presentation right here. Next week we have James McConnell and Ojelabi Oriumi. They will be speaking on Kamamo Almada rifted passive margin and also the ridges along the Andean margin using B-wave tomography. See you next Friday. And if anyone have question, you can reach back to Daniella and to Juan Pablo. Thank you for attending.
Thank you, Mohammed. Thank you, everyone.